Welcome back. Connecting to our previous topic, we should think about the forces between molecules for this session. So if we imagine we've got some water. Water is a good example of a molecule because it does everything. It's an unusual example to choose for this because water is very complicated, but in positive things we can have an example of everything here. So our water molecule will interact with other water molecules in a variety of ways, and that is what we want to investigate. So we will have another water molecule here, and there will be some kind of force between them holding them together, otherwise our water would just be a gas. So let us jump away from water and make it simple to start with and go up in stages. The simplest type of bonding or interaction that we can think of is between ions, because it's just simply an electric charge attracting another electric charge, and those are reasonably familiar to us as people with experience of the world. So if we take a positively charged surface and a negatively charged surface, they attract each other on a macroscopic scale, and we can imagine that an ion, for example a sodium ion, Na+, will attract a chloride ion. And indeed, if we look at some normal table salt, that is exactly what they're doing. The positive ions and the negative ions have organized themselves into a structure very much like this, but in 3 dimensions, so that the positives and negatives can get as close to each other as possible, and from outside there's very little charge left over. This is called, this is electrostatic interaction, but they're on the order of single charges. If we were thinking of it on a macroscopic scale, we would get something like this pen and charge it up by rubbing it with a piece of fluff, oops, like this, and then we would get a charge and we could use it to attract or repel things. This is relatively simple, and you may have encountered it in physics. The force goes down with the square of the distance. I've called it x for distance, but I'm going to change it. So force, this is a proportional to sign, 1 divided by, because it gets smaller, the distance, and let's call the distance r. R is a radius because it doesn't matter which direction it is. So it's useful to use r for radius because it doesn't make any difference whether it's pointing downwards or across or upwards, it's exactly the same force. Also in physics you will have encountered the other things in here, so we will have the 2 charges, the positive charge and the negative charge. So the 2 charges divided by the square of the distance, and then we'd have some kind of constant in there, the constant of charge to force. Now we can go to the next type of force, which is if we take a molecule that has a charge on both ends, let's make it plus and minus, it behaves very much like a magnet. So our molecule will then attract another molecule and they will align. This is what happens if we have a charge distribution in our molecule, and they don't stay stuck to each other in a liquid. In solid they would stay in this orientation, but in the liquid they will rotate. But most of the time they will be facing in an advantageous direction, so they'll be going along together and then both lip, and that will tend to make an interaction, a positive interaction between the two, so they tend to stick together. This develops naturally if we have a bond. Let's take hydrogen chloride. We have a bond where the electrons are unevenly distributed. So if we have hydrogen chloride, the chlorine has an unfair share of the electrons. We can draw it like that. So the hydrogen has a little plus charge and the chlorine has a little minus charge, but it's not a full charge, so we draw that also with a delta, but this time with a little delta. So we had deltas last time for changes of, that's a capital delta, that's an actual change of something. Little delta means a very tiny change of something. I couldn't draw it from that angle, but here we are. If we now go to our water, it's doing the same thing. So the water has an oxygen in the middle and 2 hydrogens. And in the same way, the oxygen dominates the bond and pulls some of the electron density. This makes our molecule charged in the middle. If it was a straight molecule, like CO2, for example, then the two ends would be negatively charged and the middle positive. But if we're looking at that from far away, it doesn't look like it's charged at all. The total charge is balanced. So only in a bent molecule, if we have a charge in the middle, can we generate a dipole, which looks like this, so plus and minus. And that will be in the direction of the charge, which is this way. So these two are invisible from further away, but the dipole is from the back of the molecule to the front pointy bit. It's like a little gull flying. Obviously, if we dissolve salt in water, the ions of the salt can interact with the dipole of the water. So if we have the sodium ion, it will interact with the negative end of the dipole, and that will generate a dipole ion interaction, which comes in this gap here. Then comes the weakest type of force, but which is much weaker than the others, but it is always there. If we take a gas such as argon, it can't do any of these types of interactions because it doesn't have a dipole. In fact, any pure element can't do that because it doesn't have a dipole. Looking at ideal gases, we can dig out some general knowledge. We know that the boiling point of helium is much lower than the boiling point of argon, and that tells us two things. It tells us, first of all, there is a force between these gas molecules, because otherwise they wouldn't form a liquid ever, and also that the strength of that force goes up with the size or mass of the atom. Helium has only got 2 protons, 2 neutrons, 2 electrons, and argon is right down near the bottom of the periodic table. It's not the heaviest, but it's getting on. So something is going on, and it fits with the other forces. We have our positive nucleus in here, and we have our negative electron cloud. And the electron cloud is generally spherical, although not entirely. And then what we're going to do is apply some force. So if we bring along a charge, let's have a positive charge here, we will distort these molecules, these atoms. And what will happen is the electrons, let's have one over here too, and distort these atoms. What will happen is the electrons will be motivated to move over in this direction towards the positive charge, and the nuclei, the positive charges, will be motivated to move away in the other direction. So I haven't moved the atoms at all, I've just distorted the electron cloud, and that brought some negative charge over here, and so it has generated a dipole, which I'll now draw. So now I've rubbed off the green and put the signs on there. This is my positive charge, so it's obviously going to have a positive end, and this is the negative charge, it's going to have a negative end. Now we can see that we've generated a dipole, which is pointing in the correct direction for our ion, and that will now interact with the ion. But these dipoles can also interact with each other. So now what we can see is these two argon atoms are going to interact with each other via a dipole-dipole interaction, even though they don't normally have dipoles. We can also see why the helium is not very good at this. It's because the electrons in the helium are very close to the nucleus, and so they can't move as easily. This is like a soft jelly, and this is more like a hard ball. It's much harder for it to distort, and so the charge difference, the dipole, is very small, just because the charge is the same, but the distribution is smaller. And here we have an easier distribution, so we can stretch it further away, and then we get a bigger dipole. Obviously the number of electrons also helps, but it's mostly the stiffness of the electron cloud. So we can generate this or we can cause two atoms to attract to each other, but we would have to first of all get them moving. In reality, however, these atoms are wobbling around a bit like jelly the whole time, and they get into a kind of step. So they influence each other and tend to interact and generate a positive interaction. This type of interaction, a temporary dipole interaction, is always attractive. In fact, when we take our argon on its own, it's more likely to do a slightly different motion where it wobbles. Instead of bouncing from side to side, which would actually change the center of mass of the molecule, the electron cloud wobbles like a jelly. So it's pulsing out and in. In this state, we have a quadrupole instead of a dipole. So instead of having plus here and minus here, we have a negative charge on the ends, and because this electron cloud is thinner in this direction, we have a positive charge on the sides. As we're expecting the electron cloud to be pulsing from side to side, or like a jelly wobbling, then this will oscillate. This positive will become negative and positive, negative and positive, and the next door argon will be influenced by it. Obviously, we could have higher orders of vibration in there as well, but this will do for us. So, drawing them back out again, we can have our simple pure types, ionic bonding or ionic interaction, dipole-dipole interaction, and these temporary dipoles interacting with each other. Typically we would call that van der Waals. In between these we have the mixed ones, so we've got ions interacting with dipoles, ions interacting with van der Waals, and dipoles interacting with van der Waals forces, to give us a full palette of possibilities. All of these interactions are positive apart from ionic interactions, which can be negative. In other words, they repel each other if we have two positive ions or we have two negative ions. Otherwise, they're always a positive attractive force, which is why we don't see liquids suddenly exploding into a gas in front of us, because they're always attracting. What we've missed, however, is the top force, which is a special one. Looking at our water, we can see that it's bent, and we have to explain that before we can get any further. So instead of being in a spherical pattern, the electrons are in orbitals, and they're in a shape like this. And there are four of these. So there's one pointing towards this hydrogen, one pointing towards this hydrogen, and one pointing up here, and one down below. Let's have it underneath. It's a tetrahedron, a symmetrical shape, and the little back lobes we'll not worry about too much right now, because they're not important to us for this purpose. The hydrogen electrons are in a spherical orbital, and so they're fine. When we mix these together to make the bond, then we generate some electron density here in between the two, which is what forms the bond holding the hydrogen to the oxygen. So that was a complicated way of saying the electrons in here are hanging around between the oxygen and hydrogen, but there are two other orbitals which also have electrons in them, up here and down below. Make that one red, maybe. And those electrons are ready to do something. It's an electron pair, and maybe we can draw it in the simpler Bohr model. So this is the Bohr atomic model, where we have 8 electrons in the outer shell of the oxygen, and 4 of them in 2 pairs are bonded to the hydrogen. Because it's in 3 dimensions and not in 2 like in this diagram, we have a tetrahedron where these two have an angle of about 110 degrees and these two also have an angle of about 110 degrees but flipped 90 degrees. Not flat like that. This is what it really looks like. And we've got much the same situation, so that's good. Quantum mechanics and simple models agree on the shape, and they also agree that there's some electrons over here that are going to do something interesting. So now we can have two molecules near to each other. We've got the lone pair, the pair of electrons that aren't attached to anything, here, and they can interact with this hydrogen. If they do that, they can potentially form a bond, so they can steal the hydrogen off this water, and that would be by giving those two electrons to the hydrogen, and the hydrogen will give its two electrons from the bond back to the oxygen. Let me show you what happens there by rubbing it out. So now we've formed a new bond to this hydrogen. Obviously it's going to move closer to here, and we've formed an H3O+, and we've also formed an OH- because we've stolen the hydrogen but we haven't taken its electrons, so that's now become negative. So we formed an H+ and an OH- effectively. In water this process is going on all the time, and the OH- can steal it back. So if we catch it stealing it back and giving it, then it is the same as a bond, effectively. It is partially forming and partially breaking the whole time, and it behaves like the water is stuck together much stronger than it would otherwise be. It's a special type of bonding called hydrogen bonding, and it happens mostly with hydrogen, and only if the hydrogen is connected to another atom that also has a lone pair and also pulls the electrons away from the hydrogen to make a positive charge. That allows it to steal the electrons completely and also to steal the hydrogen completely. And that causes them to stick together. So it's typically oxygen containing and nitrogen containing molecules that can do this, otherwise not. And that's why water is special. This leads us to an emerging property of matter, that when we get to the end of a contiguous material, something weird happens. So if we're in the middle of our water, the water molecules are surrounded by other water molecules, and they're doing hydrogen bonding, and they're doing dipole-dipole interaction, and they're doing van der Waals interaction with each other, and that causes them to have a lower energy than they would otherwise have in the gas phase. That's why they're a liquid, and that's good. But then we come to our surface molecules, and they are missing half of their world. Half of the atoms are air or space. There's a lot of gap between atoms in a gas. That means that there is a lot higher energy in those molecules at the surface, and that manifests itself as surface tension, as a force that tries to make the surface area of the surface lower. This reveals why superheating happens during boiling, because we have to generate new surface area, and that costs us all the bonding energy between the molecules, and so to get it to start boiling is difficult. Even in freezing, where we have a solid forming, the same thing happens, that we have to generate a new interface between the solid material and its liquid, and that costs energy, and so starting it is very difficult. If we have very pure water and very clean sides, it's difficult to do that, and so we can undercool our water to -9, sometimes even more. I have a couple of demonstration videos of boiling and cooling, including superheating during boiling and supercooling in freezing, so you can have a look at those. And we'll stop there for today. Goodbye.